This is a chapter on sound. Some marine animals, such as dolphins, use sound waves to locate distant objects. In this process, called echolocation, a dolphin produces a rapid train of short sound pulses that travel through the water, bounce off distant objects, and reflect back to the dolphin. From these echoes, dolphins can determine the size, shape, speed, and distance of their potential prey. The dolphins shown in this photograph are bottlenose dolphins in captivity in Hawaii. Dolphins use sound for navigation, communication, and echolocation. A variety of other marine mammals and most bats also use sound waves to echolocate. Chapter 12 Overview. First section, sound waves, explains how sound waves are produced, explores the basic characteristics of sound waves, and introduces the Doppler effect. Sound intensity and resonance, explains how to calculate intensity, relates intensity, decibel level, and perceived loudness, and explores the phenomena of resonance. Harmonics introduces standing waves on a vibrating string and in open and closed pipes, calculates harmonics, relates harmonics to timbre, and discusses how beats occur. Knowledge to review. Longitudinal waves are waves in which the particles vibrate parallel to the direction of wave motion. Wave speed is equal to the product of wavelength and frequency. Standing waves are formed when two waves of the same frequency, amplitude, and wavelength travel in opposite directions through a medium and interfere with each other. Next, we'll look at items to probe. Familiarity with wave-related phenomena asks students to describe how sound travels between a speaker and a listener. Preconceptions about pitch and loudness ask students what determines the pitch and loudness associated with a sound. Chapter Preview. There are three sections. The first section, sound waves, is broken into three subsections: the production of sound waves, characteristics of sound waves, and the Doppler effect. Section 2, sound intensity and resonance, is broken into sound intensity and forced vibrations and resonance. Harmonics is the third section, standing waves on a vibrating string, standing waves in a air column, and the third subsection is beats. What to expect? In this chapter, you will study many physical aspects of sound, including the nature of sound waves, frequency, intensity, resonance, and harmonics. Why it matters. Some animals, including dolphins and bats, use sound waves to learn about their prey. Musical instruments create a variety of pleasing sounds through different harmonics. Objectives for Section 1: explain how sound waves are produced, relate frequency and pitch, compare the speed of sound in various media, relate plane waves to spherical waves, recognize the Doppler effect, and determine the direction of a frequency shift when there is a relative motion between a source and an observer. Figure 1a, the sound from a tuning fork is produced by B, the vibrations of each of its prongs. C, when a prong swings to the right, there is a region of high density and pressure. D, when the prong swings back to the left, a region of lower density and pressure exists. The production of sound waves. Whether a sound wave conveys the shrill whine of a jet engine or the melodic whistling of a bird, it begins with a vibrating object. We will explore how sound waves are produced by considering a vibrating tuning fork as shown in figure 1A. The vibrating prong of a tuning fork, shown in figure 1B, sets the air molecules near it in motion. As the prong swings to the right, as in figure 1C, the air molecules in front of the movement are forced closer together. This situation is exaggerated in the figure for clarity. Such a region of high molecular density and high air pressure is called a compression. Compression, the region of a longitudinal wave in which the density and pressure are at a maximum. As the prong moves to the left, as in figure 1D, the molecules to the right spread apart, and the density and air pressure in this region become lower than normal. This region of lower density and pressure is called a rarefaction. Rarefaction, the region of a longitudinal wave in which the density and pressure are at a minimum. Figure 2A, as this tuning fork vibrates, B, a series of compressions and rarefactions moves away from each prong. C, the crests of the sine wave correspond to compressions and the troughs to rarefactions. Sound waves are longitudinal. In sound waves, the vibrations of air molecules are parallel to the direction of wave motion. Thus, sound waves are longitudinal. The simplest longitudinal wave produced by a vibrating object can be represented by a sine curve. In figure 2, the crests correspond to compressions, regions of higher pressure, and the troughs correspond to rarefactions, regions of lower pressure. Point out that some of the individuals may be able to hear sound slightly below 20 hertz and above 20,000 hertz, because the range of frequencies defined as audible is based on the ability of the average human ear. As you get older, that range decreases. As the tuning fork continues to vibrate, a series of compressions and rarefactions forms and spreads away from each prong. These compressions and rarefactions spread out in all directions, like ripple waves in a pond. When the tuning fork vibrates with simple harmonic motion, the air molecules also vibrate back and forth with simple harmonic motion. Thus, the sine curve represents the changes in air pressure due to the propagation of sound waves. Note that figure 2 shows an idealized case. This example disregards energy losses that would decrease the wave amplitude. Elephants use infrasonic waves to communicate with one another. Their large ears enable them to detect these low frequency sound waves, which have relatively long wavelengths. Elephants can effectively communicate this way even when they are separated by many kilometers. Characteristics of sound waves. As discussed earlier, frequency is defined as the number of cycles per unit of time. Sound waves that the average human ear can hear, called audible sound waves, have frequencies between 20 and 20,000 hertz. An individual hearing depends on a variety of factors, including age and experiences with loud noises. Sound waves with frequencies less than 20 hertz are called infrasonic waves, and those above 20,000 hertz are called ultrasonic waves. It may seem confusing to use the term sound waves for infrasonic or ultrasonic waves because humans cannot hear these sounds, but these waves consist of the same types of vibrations as the sounds that we can hear. The range of audible sound waves depends on the ability of the average human ear to detect their vibrations. Dogs can hear ultrasonic waves that humans cannot. Frequency determines pitch. The frequency of an audible sound wave determines how high or low we perceive the sound to be, which is known as pitch. Pitch is a measure of how high or low a sound is perceived to be, depending on the frequency of the sound wave. As the frequency of a sound wave increases, the pitch rises. The frequency of the wave is an objective quantity that can be measured, while pitch refers to how different frequencies are perceived by the human ear. Pitch depends not only on the frequency, but also on other factors such as background noise and loudness. Ultrasonic images. Ultrasonic waves can be used to produce images of objects inside the body. Such imaging is possible because sound waves are partially reflected when they reach a boundary between two materials of different densities. This is actually an ultrasonic image. Fascinating. The images produced by ultrasonic waves are clearer and more detailed than those that can be produced by lower frequency sound waves because the short wavelengths of ultrasonic waves are easily reflected off small objects, such as here you see a ultrasonic image of the abdomen of an individual. Audible and infrasonic sound waves are not as effective because their longer wavelengths pass around small objects. In order for ultrasonic waves to see an object inside the body, the wavelength of the waves used must be about the same size or smaller than the object. Again, this is a echocardiogram. A typical frequency used in an ultrasonic device is about 10 megahertz. The speed of an ultrasonic wave in human tissue is about 1,500 meters per second. So the wavelength of 10 megahertz travels is about 0.15 millimeter. A 10 megahertz ultrasonic device will not detect objects smaller than this size. So if you're looking for a small tumor, you may want to use a very, very high frequency sound. Physicians commonly use ultrasound waves to observe fetuses. In this process, a crystal emits ultrasonic pulses. The same crystal acts as a receiver and detects the reflected sound waves. These reflected sound waves are converted to an electrical signal, which forms an image on a fluorescent screen. By repeating this process for different portions of the mother's abdomen, a physician can obtain a complete picture of the fetus, as shown above. These images allow doctors to detect some types of fetal abnormalities. Here is Table 1, speed of sounds in various media. Speed of sound depends on the medium. Sound waves can travel through solids, liquids, and gases because waves consist of particle vibrations. The speed of the wave depends on how quickly one particle can transfer its motion to another particle. For example, solid particles respond more rapidly to a disturbance than gas particles do because the molecules of a solid are closer together than those of a gas are. As a result, sound waves generally travel faster through solids than through gases. Table 1 shows the speed of sound waves in various media. The speed of sound also depends on the temperature of the medium. As the temperature rises, the particle of gas collide more frequently. Thus, in a gas, the disturbance can spread faster at higher temperatures than at lower temperatures. In liquids and solids, the particles are close enough together that the difference due to temperature changes is less noticeable. Sound waves propagate in 3 dimensions. In the chapter Vibrations and Waves, waves are shown as traveling in a single direction, but sound waves actually travel away from a vibrating source in all 3 directions, as does light. When a musician plays a saxophone in the middle of a room, the sound can be heard throughout the room because the sound waves spread out in all directions. The wave fronts of sound waves spreading in 3 dimensions are approximately spherical. To simplify, we shall assume that the wave fronts are actually spherical unless stated otherwise. In this representation of a spherical wave, the wave fronts represent compressions, and the rays show the direction of the wave motion. Each wave front corresponds to a crest of the sine curve. In turn, the sine curve corresponds to a single ray. Spherical waves can be represented graphically in 2 dimensions with a series of circles surrounding the source as shown in Figure 3. The circles represent the centers of compression, called wave fronts, because we are considering a 3-dimensional phenomena in 2 dimensions. Each circle represents a spherical area. Because each wave front locates the center of a compression, the distance between adjacent wave fronts is equal to 1 wavelength, lambda. The radial lines perpendicular to the wave fronts are called rays. Rays indicate the direction of the wave motion. The sine curve used in our previous representation of sound waves, also shown in Figure 3, correspond to a single ray. Figure 4, spherical wave fronts that are a great distance from the source can be approximated with parallel planes known as plane waves. Because crests of the sine curve represent compressions, each wave front crossed by this ray corresponds to a crest of a sine curve. Now consider a small portion of a spherical wave front that is many wavelengths away from its source as shown in Figure 4. In this case, the rays are nearly parallel lines, and the wave fronts are nearly parallel planes. Thus, at distances from the source that are great relative to the wavelength, we can approximate spherical wave fronts with parallel planes. Such waves are called plane waves. Any small portion of a spherical wave that is far from the source can be considered a plane wave. Plane waves can be treated as one-dimensional waves all traveling in the same direction, as in the chapter Vibrations and Waves. Conceptual challenge. 1. Music from a trumpet. Suppose you hear music being played from a trumpet that is across the room from you. Compressions and rarefactions from the sound waves reach your ear, and you interpret these vibrations as sound. Were the air particles that are vibrating near your ear carried across the room by the sound wave? How do you know? And 2, lightning and thunder. Light waves travel nearly 1 million times faster than sound waves in air. With this in mind, explain how the distance to a lightning bolt can be determined by counting the seconds between the flash and the sound of thunder. All right, the answers. 1. Music from a trumpet. No. As with all waves, the disturbance travels, not the material itself. Individual air molecules do not move across the room with the sound wave. Instead, each molecule vibrates in place, and the vibrations are transferred from one particle to the next. Lightning and thunder. Because light travels so much faster than sound, the speed of light can be considered to be effectively infinite in this case, and the flash is considered to have occurred at the same instant we see it. Thus, the time it takes the sound wave to travel or to reach the listener multiplied by the speed of sound in air gives the approximate distance between the observer and the lightning bolt. Figure 5, as this ambulance moves to the left, observer A hears the siren at a higher frequency than the driver does, while observer B hears a lower frequency. Two things. You can go on YouTube and find demonstrations, and the driver of the ambulance hears absolutely no change in the siren. The Doppler effect. If you stand on the street while an ambulance speeds by with its siren on, you will notice the pitch of the siren change. The pitch will be higher as the ambulance approaches and will be lower as it moves away. As you read earlier in this section, the pitch of a sound depends on its frequency. But in this case, the siren is not changing its frequency. How can we account for this change in pitch? Relative motion creates a change in frequency. If a siren sounds in a parked ambulance, an observer standing on the street hears the same frequency that the driver hears, as you would expect. When an ambulance is moving, as shown in Figure 5, there is a relative motion between the moving ambulance and a stationary observer. This relative motion affects the way the wavefront of the sound waves produced by the siren are perceived by an observer. For simplicity's sake, we will assume that the sound waves produced by the siren are spherical. Some students may think that the observed frequency rises as the source of sound approaches an observer and decreases as the source moves away. Stress the fact that the observed frequency is higher or lower and that it changes only when the source passes the observer. This concept is illustrated in Figure 5, which shows that the distance between wavefronts is constant for each observer. The amplitude will change. That's what's confusing people. Although the frequency of the siren remains constant, the wavefront reaches an observer in front of the ambulance, observer A, more often than it would if the ambulance were stationary. The reason is that the source of the sound wave is moving towards the observer. The speed of sound in the air does not change because the speed depends only on the temperature of the air. Thus, the product of wavelength and frequency remains constant. Because the wavelength is less, the frequency heard by observer A is greater than the source frequency. For the same reason, the wavefront reaches the observer behind the ambulance, observer B, less often than they would if the ambulance were stationary. As a result, the frequency heard by observer B is less than the source frequency. The frequency shift is known as the Doppler effect. Doppler effect, an observed change in frequency when there is relative motion between the source of the wave and an observer. The Doppler effect is named for Austrian physicist Christian Doppler, 1803 to 1853, who first described it. Study the illustrations below. They will help you understand. And don't forget, the driver of the car, the police car and the ambulance, here's no Doppler effect. The sound is constant frequency. We have considered a moving source with respect to a stationary observer, but the Doppler effect also occurs when the observer is moving with respect to a stationary source, or when both are moving at different velocities. In other words, the Doppler effect occurs whenever there is relative motion between the source of waves and an observer. If the observer is moving instead of the source, the wavelength in air does not change, but the frequency at which waves arrive at the ear is altered by the motion of the ear relative to the medium. Although the Doppler effect is most commonly experienced with sound waves, it is a phenomena common to all waves, including electromagnetic waves such as visible light. Section review. What is the relationship between frequency and pitch? A greater frequency is perceived as a higher pitch. Two, dolphin echolocation is similar to ultrasound. Reflected sound waves allow a dolphin to form an image of the object that reflected the waves. Dolphins can produce sound waves with frequencies ranging 0.25 kilohertz to 220 kilohertz, but only those at the upper end of the spectrum are used in echolocation. Explain why high frequency waves work better than low frequency waves. Higher frequencies function well in echolocation because their relatively short wavelengths are able to detect smaller objects. Longer wavelengths would disperse around small objects. Sound pulses emitted by a dolphin travel through 20 degrees Celsius ocean water at a rate of 1,450 meters per second. In 20-degree air, these pulses would travel 342.9 meters per second. How can you account for this difference in speed? Sound waves travel faster through water than through air because the molecules of water are closer together and, as a result, can spread vibrations more quickly. Could a portion of the innermost wave front shown in Figure 6 be approximated by a plane wave? Why or why not? No. The wave front must be far from the source relative to the wavelength to be approximated by plane waves. Figure 7 is a diagram of the Doppler effect in a ripple tank. In which direction is the source of these ripple waves moving? To the right. If the source of the waves in Figure 7 is stationary, which way must the ripple tank be moving? To the left. As a dolphin swims toward a fish, the dolphin sends out sound waves to determine the direction the fish is moving. If the frequency of the reflected waves is higher than that of the emitted waves, is the dolphin catching up to the fish or falling behind? The dolphin is catching up to the fish. Uh-oh. Objective, Section 2, sound intensity and resonance. Calculate the intensity of sound waves. Relate intensity, decibel level, and perceived loudness. Explain why resonance occurs. Figure 8. As a piano wire vibrates, it transfers energy to the piano's soundboard, which in turn transfers energy into the air in the form of sound intensity. When a piano player strikes a piano key, a hammer inside the piano strikes a wire and causes it to vibrate, as shown in Figure 8. The wire's vibrations are then transferred to the piano soundboard. As the soundboard vibrates, it exerts a force on air molecules around it, causing the air molecules to move. Because this force is exerted through displacement of the soundboard does work on the air. Thus, as the soundboard vibrates back and forth, its kinetic energy is converted into sound waves. This is one reason that the vibration of the soundboard gradually dies out. Intensity is the rate of energy flow through a given area. As described in Section 1, sound waves traveling in air are longitudinal waves. As the sound waves travel outward from the source, energy is transferred from one air molecule to the next. The rate at which this energy is transferred through a unit area of the plane wave is called the intensity of the wave. Intensity, the rate at which energy flows through a unit area perpendicular to the direction of wave motion. Because power, P, is defined as the rate of energy transfer, intensity can also be described in terms of power. Intensity equals delta E divided by delta T all over area equals power divided by area equals power divided by 4 pi r squared. Notice the radius squared in the denominator. Some students may have trouble distinguishing between energy and the rate of energy transfer or power. Briefly review the idea of power introduced in the chapter Work and Energy to make sure this distinction is clear to students before intensity is introduced. The SI unit for power is the watt. Thus, intensity has units of watts per square meter. In a spherical wave, energy propagates equally in all directions. No one direction is preferred over any other. In this case, the power emitted by the source P is distributed over a spherical surface, area equals 4 pi r squared, assuming that there is no absorption in the medium. That would change things. This equation shows that the intensity of a sound wave decreases as the distance from the source increases. This occurs because the same amount of energy is spread over a larger area. So we have intensity equals power over 4 pi r squared. Problem A. Or intensity equals power divided by the product 4 pi and the distance from the source squared. So the intensity will decrease rapidly. It's not a linear decrease. If a mass of 0.55 kilograms attached to a vertical spring stretches the spring 2.0 centimeters from its original equilibrium position, what is the spring constant? Here's given. Notice you have kilograms and meters and G as well. So everything is set to be plugged in to the equation, which we basically have already used. And the equation is going to be calculate the intensity of the sound waves from an electric guitar's amplifier at a distance of 5 meters when its power output is equal to each of the following values. A, 0.25 watts. Write down what we're given. It's 5 meters. There's the intensity equation and plug in. The answer is 8 times 10 to the negative fourth watts per square meter. Now do 0.5 watts, and again, plug in, same exact problem, carbon copy except for the answer, and there's the answer. Make sure your scientific notation is correct. See if you can see a pattern among the three values that are given, and see how the intensity is changing. And that's 6.4 times 10 to the negative fourth. At a maximum level of loudness, the power output of a 75-piece orchestra radiated as a sound of 70 watts. What is the intensity of these sound waves to a listener who is sitting 25 meters from the orchestra? All right, that's what's given. That is the equation. That is the plug-in expression, and that is the answer. 8.91 times 10 to the negative 3 watts per square meter. If the intensity of a person's voice is 4.6 times 10 to the negative 7th watts per meter squared at a distance of 2 meters, how much sound power does that person generate? There is the given values, and that's the equation, and that's the plug-in expression, and that's it. 2.3 times 10 to the negative 5th watts. How much power is radiated as sound from a band whose intensity is 1.6 times 10 to the negative 3 watts per square meter at a distance of 15 meters? Intensity, 1.6 times 10 to the negative 3 watts per square meter, radius of 15 meters. There's the equation. Let's plug in and calculate. 4.5 watts. The power output of a tuba is 0.35 watts. At what distance is the sound intensity of the tuba 1.3 times 10 to the negative 3 watts per meter squared? There's what's given. There is the equation. There's the plug-in expression. And there it is, 4.8 meters. Intensity and frequency determine which sounds are audible. As you saw in section 1, the frequency of sound waves heard by the average human ranges from 20 to 20,000 hertz. Intensity is also a factor in determining which sound waves are audible. Figure 9 shows how the range of audibility of the average human ear depends on both frequency and intensity. As you can see in this graph, sounds at low frequencies, those below 50 hertz, or high frequencies, those above 12,000 hertz, must be relatively intense to be heard, whereas sounds in the middle of the spectrum are audible at lower intensities. The softest sounds that can be heard by the human ear occur at a frequency of about 1,000 hertz and an intensity of 1.0 times 10 to the negative 12 watts per square meter. Such a sound is said to be at the threshold of hearing. Figure 9. Human hearing depends on both the frequency and the intensity of sound waves. Sounds in the middle of the spectrum of frequencies can be heard more easily at lower intensities than those at lower and higher frequencies. Note that some humans can hear slightly softer sounds at a frequency of about 3,300 hertz. The threshold of hearing at each frequency is represented by the lowest curve in figure 9. Misconception alert. The relationship between frequency, intensity, and audibility is complex and often confusing to students. Stress that neither frequency nor intensity alone can determine which sounds are audible. Both factors must be taken into account. For frequencies near 1000 Hz and at the threshold of hearing, the changes in pressure due to compression and rarefaction are about 3/10 billionths of atmospheric pressure. The maximum displacement of air molecules at the threshold of hearing is approximately 1 times 10 to the negative 11th meter. Comparing this number to the diameter of a typical air molecule, which is about 1 times 10 to the negative 10th meters, reveals that the ear is an extremely sensitive detector of sound waves. The loudest sound that a human ear can tolerate have an intensity of about 1 watt per square meter. A 75-piece orchestra produces 75 watts at its loudest. This is comparable to the power required to keep one medium-sized electric light bulb burning. Speech has even less power. It would take the conversation of about 2 million people to provide the amount of power required to keep a 50-watt light bulb burning. This is known as the threshold of pain because sounds with greater intensities can produce pain in addition to hearing. The highest curve in figure 9 represents the threshold of pain at each frequency. Exposure to sounds above the threshold of pain can cause immediate damage to the ear, even if no pain is felt. Prolonged exposure to sounds at lower intensities can also damage the ear. For this reason, many musicians wear earplugs during their performances. Note that the threshold of hearing and the threshold of pain merge at both high and low ends of the spectrum. Here are some figures that you can study. Relative intensity is measured in decibels. Just as the frequency of a sound wave determines its pitch, the intensity of a wave approximately determines its perceived loudness. However, loudness is not directly proportional to intensity. The reason is that the sensation of loudness is approximately logarithmic in the human ear. Relative intensity is the ratio of the intensity of a given sound wave to the intensity at the threshold of hearing. Because of the logarithmic dependence of perceived loudness on intensity, using a number equal to 10 times the logarithm of the relative intensity provides a good indicator for human perceptions of loudness. The measure of loudness is referred to as the decibel level. Here is table 2. Please study it carefully. Here is a continuation of table 2. Continue to study it carefully. The decibel level is dimensionless because it is proportional to the logarithm of a ratio. A dimensionless unit called the decibel is used for values on the scale. A decibel, a dimensionless unit that describes the ratio of two intensities of sound. The threshold of hearing is commonly used as the reference intensity. The conversion of intensity to decibel level is shown in table 2. Notice in table 2 that when the intensity is multiplied by 10 decibels are added to the decibel level. A given difference in decibels corresponds to a fixed difference in perceived loudness. Although much more intensity, as in 0.9 watts per square meter, is added between 110 and 120 decibels than between 10 and 20 decibels, 9 times 10 to the negative 11th watts per square meter. In each case, the perceived loudness increases by the same amount. The original unit of decibel level is the bell, named in honor of Alexander Graham Bell, the inventor of the telephone. The decibel is equivalent to 0.1 bell. Here are some convenient references for decibels below. Figure 10. If one blue pendulum is set in motion, only the other blue pendulum, whose length is the same, will eventually oscillate with a large amplitude or resonant. Forced vibrations and resonance. When an isolated guitar string is held taut or plucked, hardly any sound is heard. When the same string is placed on a guitar and plucked, the intensity of the sound increases dramatically. What is responsible for this difference? To find the answer to this question, consider a set of pendulums suspended from a beam and bound by a loose rubber band as shown in figure 10. If one of the pendulums is set in motion, its vibrations are transferred by the rubber band to the other pendulums, which will also begin vibrating. This is called a forced vibration. The vibrating strings of a guitar force the bridge of the guitar to vibrate, and the bridge in turn transfers its vibrations to the guitar body. These forced vibrations are called sympathetic vibrations because the guitar body has a larger area than the strings do. It enables the strings' vibration to be transferred to the air more efficiently. As a result, the intensity of the sound is increased and the strings' vibrations die out faster than they would if they were not attached to the body of the guitar. In other words, the guitar body allows the energy exchange between the strings and the air to happen more efficiently, thereby increasing the intensity of the sound produced. In an electric guitar, string vibrations are translated into electrical impulses which can be amplified as much as desired. An electric guitar can produce sounds that are much more intense than those of an unamplified acoustic guitar, which uses only the forced vibrations of the guitar's body to increase the intensity of the sound from the vibrating strings. Vibration at the natural frequency produces resonance. As you saw in the chapter on waves, the frequency of a pendulum depends on the string length. Thus, every pendulum will vibrate at a certain frequency, known as its natural frequency. In figure 10, the two blue pendulums have the same natural frequency, while the red and green pendulums have different natural frequencies. When the first blue pendulum is set in motion, the red and green pendulums will vibrate only slightly. But the second blue pendulum will oscillate with a much larger amplitude because its natural frequency matches the frequency of the pendulum that was initially set in motion. Figure 11, on November 7, 1940, the Tacoma Narrows Suspension Bridge collapsed just 4 months after it opened. Standing waves caused by strong winds set the bridge in motion and led to the collapse. Here's another picture of it. Quite dramatic. There are films on YouTube that you can access to actually see the bridge swaying back and forth with the wind. This system is said to be in resonance, a phenomena that occurs when the frequency of a force applied to a system matches the natural frequency of vibration of the system, resulting in a large amplitude of vibration. Because energy is transferred from one pendulum to the other, the amplitude of vibration of the first blue pendulum will decrease as the second blue pendulum's amplitude increases. A striking example of structural resonance occurred in 1940 when the Tacoma Narrows Bridge in Washington, the state of Washington, shown in Figure 11, was set in motion by the wind. High winds set up standing waves in the bridge, causing the bridge to oscillate at one of its natural frequencies. The amplitude of the vibrations increased until the bridge collapsed. A more recent example of structural resonance occurred during the Loma Prieta earthquake near Oakland, California in 1989, when part of the upper deck of a freeway collapsed. The collapse of this particular section of roadway has been traced to the fact that the earthquake waves had a frequency of 1.5 hertz, very close to the natural frequency of that section of roadway. Conceptual challenge. 1. Concert. If a 15-person musical ensemble gains 15 new members so that its size doubles, will a listener perceive the music created by the ensemble to be twice as loud? Why or why not? 2. A noisy factory. Federal regulations require that no office or factory worker be exposed to noise levels that average above 90 decibels over 8-hour day. Thus, a factory that currently averages 100 decibels must reduce their noise level by 10 decibels. Assuming that each piece of machinery produces the same amount of noise, what percentage of equipment must be removed? Explain your answer. 1. The concert. No. The intensity doubles, but loudness is not directly proportional to intensity. And 2. A noisy factory. Reducing the decibel level by 10 requires reducing the intensity by a factor of 10. Thus, 90% of the equipment must be removed. Additional conceptual challenge. 3. Broken crystal. Opera singers have been known to set crystal goblets in vibration with their powerful voices. In fact, an amplified human voice can shatter the glass, but only at certain fundamental frequencies. Speculate about why only certain fundamental frequencies will break the glass. 4. Electric guitars. Electric guitars, which use electric amplifiers to magnify their sound, can have a variety of shapes, but acoustic guitars all have the same basic shape. Explain why. Answers. 3. Broken crystal. Only frequencies that match one of the natural frequencies of the glass can establish a resonance condition. Only then can the vibrations become large enough to shatter the goblet. Electric guitar. The body of an acoustic guitar is designed so that it can transmit the strings' vibrations to the air efficiently. The guitar's particular shape also determines the characteristic sound that distinguishes the guitar from similar instruments, such as banjos and lutes. Because the vibrations of an electric guitar strings are converted into electrical signals, there are fewer restrictions on the electric guitar's shape. Figure 12. Sound waves travel through the 3 regions of the ear and are then transmitted to the brain as impulses through nerve endings on the basilar membrane. Please study the ear carefully. We shall discuss it in detail during class. The human ear transmits vibrations that cause nerve impulses. The human ear is divided into 3 sections, outer, middle, and inner, as shown in Figure 12. Sound waves travel down the ear canal and the outer ear. The ear canal terminates at a thin, flat piece of tissue called the eardrum. The eardrum vibrates with the sound waves and transfers these vibrations to the three small bones of the middle ear, known as the hammer, anvil, and stirrup. These bones, in turn, transmit the vibrations to the inner ear, which contains a snail shaped tube about 2 centimeters long called the cochlea. The basilar membrane runs through the coiled cochlea, dividing it roughly in half. The basilar membrane has different natural frequencies at different positions along its length, according to the width and thickness of the membrane at that point. Sound waves of varying frequencies resonate at different spots along the basilar membranes, creating impulses in hair cells, specialized nerve cells embedded in the membrane. These impulses are then sent to the brain, which interprets them as sounds of varying frequencies. Section review number 1. When the decibel level of traffic in the street goes from 40 to 60 decibels, how much greater is the intensity of the noise? The intensity is increased by a factor of 100. Consider that. If two flutists play their instruments together at the same intensity, is the sound twice as loud as that of either flautist playing alone at that intensity? Why or why not? No, because the sensation of loudness is approximately logarithmic in the human ear. A tuning fork consists of two metal prongs that vibrate at a single frequency when struck lightly. What will happen if a vibrating tuning fork is placed near another tuning fork at the same frequency? Explain. The second tuning fork will pick up the vibrations of the first tuning fork, and a faint sound will be heard from the second fork. This occurs because the two forks have the same natural frequency, which is the conditional required for resonance. A certain microphone placed in the ocean is sensitive to sounds emitted by dolphins. To produce a usable signal, sound waves striking the microphone must have a decibel level of 10 decibels. If dolphins emit sound waves with a power of 0.050 watts, how far can a dolphin be from the microphone and still be heard? Assume the sound waves propagate spherically and disregard absorption of the sound waves. Intensity at 10 decibels equals 1 times 10 to the negative 11th watts per square meter. See Table 2 of this chapter in the textbook. Now, the power from the question is 0.050 watts. The intensity is also listed above as 1.0 times 10 to the negative 11th watts per square meter. Now, what we need is an equation, which is from the text. That's the equation. Now, we simply want to plug in the power, which is listed, and the intensity, which is also listed, and that will determine the radius. So there is the plug-in, and the radius is 2 times 10 to the 4th meters. 2 times 10 to the 4th meters, quite a distance away. Okay, let's look at changes. Which of the following factors change when a sound gets louder? Which change when a pitch gets louder? All right, so I have 6 different parameters: intensity, speed of the sound waves, frequency, decibel levels, wavelength, and amplitude. So let's examine which will change. It says, which of the following factors change when the sound gets louder, and which change when a pitch gets louder? So first, loudness, the intensity is correct, and decibel level. What about wavelength and amplitude? It would be the amplitude. Amplitude is very significant relative to loudness. And with pitch, it would be frequency and wavelength. All right, objectives for section 3, harmonics. Differentiate between the harmonic series of open and closed pipes. Calculate the harmonics of a vibrating string and of open and closed pipes. Relate harmonics and timbre. Relate the frequency difference between two waves to the number of beats heard per second. Figure 13, the vibrating strings of a violin produce standing waves whose frequencies depend on the string length. Standing waves on a vibrating string. As discussed in the chapter Vibrations and Waves, a variety of standing waves can occur when a string is fixed at both ends and set into vibration. The vibrations on the string of a musical instrument, such as the violin in figure 13, usually consist of many standing waves together at the same time, each of which has a different wavelength and frequency. So the sounds you hear from the stringed instrument, even those that sound like a single pitch, actually consist of multiple frequencies. Table 3 on the next page shows several possible vibrations on an idealized string. The ends of the string which cannot vibrate must always be nodes, or capital N. The simplest vibration that can occur is shown in the first row of table 3. In this case, the center of the string experiences the most displacement, and so it is an antinode. Because the distance from one node to the next is always half the wavelength, the string length L must equal lambda 1 over 2. Thus, the wavelength is twice the string length, lambda 1 equals 2L. As described in the chapter on waves, the speed of waves equals the frequency times the wavelength, which can be arranged as shown. V, or nu, equals F lambda, or F equals V, or nu, over lambda. By substituting the value for wavelength found above into this equation for frequency, we see that the frequency of this vibration is equal to the speed of the wave divided by twice the string length. Fundamental frequency equals F1, or nu over wavelength 1, or nu over 2L. You can use nu and V interchangeably. This frequency of vibration is called the fundamental frequency of the vibrating string. Fundamental frequency, the lowest frequency of vibration of a standing wave. This is table 3. Please study it carefully. It talks about the harmonic series, and you can see how it's set up. Make sure that you are familiar with it and understand it. Because frequency is inversely proportional to wavelength, and because we are considering the greatest possible wavelength, the fundamental frequency is the lowest possible frequency of a standing wave on this string. Harmonics are integral multiples of the fundamental frequency. The next possible standing wave for a string is shown in the second row of table 3. In this case, there are 3 nodes instead of 2. So the string length is equal to 1 wavelength. Because this wavelength is half the previous wavelength, the frequency of this wave is twice that of the fundamental frequency, or F2 equals 2F1. This pattern continues, and the frequency of the standing wave shown in the third row of table 3 is 3 times the fundamental frequency. More generally, the frequencies of the standing wave patterns are all integral multiples of the fundamental frequency. These frequencies form what is called a harmonic series. Harmonic series, a series of frequencies that includes the fundamental frequency and integral multiples of the fundamental frequency. The fundamental frequency corresponds to the first harmonic. The next frequency, F2, corresponds to the second harmonic, and so on. Because each harmonic is an integral multiple of the fundamental frequency, the equation for the fundamental frequency can be generalized to include the entire harmonic series. Thus, Fn equals n times F1, where F1 is the fundamental frequency, F1 equals V over 2L, and Fn is the frequency of the nth harmonic. The general form of the equation is written as follows. Harmonic series of standing waves on a vibrating string, Fn equals n times V over 2L. Frequency equals harmonic number times speed of wave on a string divided by 2 times the length of the string. If the string vibrates at one of these frequencies, the sound waves produced in the surrounding air will have the same frequency. However, the speed of these waves will be the speed of sound waves in air, and the wavelength of these waves will be that of the speed divided by the frequency. When a guitar player presses down on a guitar string at any point, the point becomes a node, and only a portion of the string vibrates. As a result, a single string can be used to create a variety of fundamental frequencies. In the equation on this page, L refers to the portion of the string that is vibrating. Figure 14, the harmonic series present in each of these organ pipes depends on whether the end of the pipe is open or closed. Standing waves in an air column. Standing waves can also be set up in a tube of air, such as the inside of a trumpet, the column of a saxophone, or the pipes of an organ like those shown in Figure 14. While some waves travel down the tube, others are reflected back upward. These waves traveling in opposite directions combine to produce standing waves. Many brass instruments and woodwinds produce sound by means of these vibrating air columns. If both ends of a pipe are open, all harmonics are present. The harmonic series present in an organ pipe depends on whether the reflecting end of the pipe is open or closed. Figure 15. In a pipe open at both ends, each end is an antinode of displacement, and all harmonics are present. Shown here are the A first, B second, and C third harmonics. When the reflecting end of the pipe is open, as illustrated in Figure 15, the air molecules have complete freedom of motion. So an antinode of displacement exists at this end. Did you know a flute is similar to a pipe open at both ends? When all keys of a flute are closed, the length of the vibrating air column is approximately equal to the length of the flute. As the keys are opened one by one, the length of the vibrating air column decreases, and the fundamental frequency increases. If a pipe is open at both ends, each end is an antinode. The situation is the exact opposite of a string fixed at both ends, where both ends are nodes. Because the distance from one node to the next, 1/2 lambda, equals the distance from one antinode to the next, the pattern of standing waves that can occur in a pipe open at both ends is the same as that of a vibrating string. Thus, the entire harmonic series is present in this case, as shown in figure 15. And our earlier equation for the harmonic series of a vibrating string can be used. Harmonic series of a pipe open at both ends, frequency equals harmonic number times speed of wave on the string divided by the product of 2 times the length of the vibrating air column. Study the equation carefully. We will use it extensively. In this equation, L represents the length of the vibrating air column. Just as the fundamental frequency of a string instrument can be varied by changing the string length, the fundamental frequency of many woodwind and brass instruments can be varied by changing the length of the vibrating air column. Figure 16, in a pipe closed at one end, the closed end is a node of displacement and the open end is an antinode of displacement. In this case, only the odd harmonics are present. The A first, B third, and C fifth harmonics are shown here. If one end of a pipe is closed, only odd harmonics are present. When one end of a organ pipe is closed, as illustrated in figure 16, the movement of air molecules is restricted at this end, making this end a node. In this case, one end of the pipe is a node and the other is an antinode. As a result, a different set of standing waves can occur, as shown in figure 16a. The simplest possible standing wave that can exist in this pipe is one for which the length of the pipe is equal to 1/4 of the wavelength. Hence, the wavelength of the standing wave equals 4 times the length of the pipe. Thus, in this case, the fundamental frequency equals the velocity divided by 4 times the pipe length. For the case shown in figure 16b, the length of the pipe is equal to 3/4 of a wavelength. So the wavelength is 4/3 the length of the pipe, as shown below. Lambda 3 equals 4/3 L. Substituting this value into the equation for frequency gives the frequency of this harmonic. Lambda 3 equals velocity over lambda 3, which equals velocity over 4/3 L, which equals 3v over 4L, which equals 3 times F1. The frequency of this harmonic is 3 times the fundamental frequency. Repeating this calculation for the case shown in figure 16c gives a frequency equal to 5 times the fundamental frequency. Thus, only odd-numbered harmonics vibrate in a pipe closed at one end. We can generalize the equation for the harmonic series of a pipe closed at one end as follows. Frequency equals harmonic number times speed of wave on the string divided by 4 times the length of the vibrating air column. Sample problem B. What are the first 3 harmonics in a 2.45 meter long pipe that is open at both ends? What are the first 3 harmonics of this pipe when one end of the pipe is closed? Assume that the speed of sound in air is 345 meters per per second. Given is the length is 2.45 meters, velocity of sound in air is 345 meters per second, as listed in the problem, and the unknown is going to be the pipe open at both ends and then the pipe closed at one end, and that's for F1, 2, and 3 for each of those. Choose the equation or situation. When the pipe is open at both ends, the fundamental frequency can be found by using the equation for the entire harmonic series. And that's Fn equals n times V over 2L, and that's where n equals 1, 2, 3, etc. When the pipe is closed at one end, use the following equation. And that's going to be Fn equals n times V over 4L, and that's for n equals 1, 3, 5, etc. In both cases, the second two harmonics can be found by multiplying the harmonic numbers by the fundamental frequency. Substitute the values into the equations and solve. For a pipe open at both ends, where L is 2.45 and V is 345 meters per second, you would plug into the equation for F1, and you're going to get 70.4 hertz. Continuing, you're going to plug in, and you're going to get, for F2, you're going to get 141 hertz, and then plug in, continue, and you're going to get 211 hertz, and then for a pipe closed at one end, F1 equals 1V over 4L, as the equation indicates, and you're going to get 35.2 hertz, 35.2 hertz. And then the next possible harmonics are the third and the fifth. And so you'll plug in again. F3 will be 106 hertz, and then for the fifth harmonic, it will be 35.2 hertz times 5, which is 176 hertz. Be sure to use the correct harmonic numbers for each situation. For a pipe open at both ends, n equals 1, 2, 3, etc. For a pipe closed at one end, only odd harmonics are present. So n equals 1, 3, 5, etc. In a pipe open at both ends, the first possible wavelength is 2L. In a pipe closed at one end, the first possible wavelength is 4L. Because frequency and wavelength are universally proportional, the fundamental frequency of the open pipe should be twice that of the closed pipe. That is, 70.4 equals 2 times 35.2. Problem set B, harmonics number 1. What is the fundamental frequency of a 0.2 meter long organ pipe that is closed at one end when the speed of sound in the pipe is 352 meters per second? Here's the equation, given the parameters. We're going to plug in right from the problem above, and you're going to get 440 hertz. A flute is essentially a pipe open at both ends. The length of the flute is approximately 66 centimeters. What are the first three harmonics of a flute when all keys are closed, making the vibrating air column approximately equal to the length of the flute? The speed of sound is 340 meters per second. All right, we list the equation, which is fairly standard by now. Plug in 260 hertz. F2 would be plug in, and you get 520 hertz. And then F3 would be plug in again 3 times 260, which is 780 hertz. What is the fundamental frequency of a guitar string when the speed of waves on the string is 115 meters per second and the effective string lengths are as follows. 0.7 meters is A, 70 centimeters or 0.7 meters. So list the equation and then plug in. (82.1 hertz), and then 0.5 meters, Again, list the equation and plug in. 115 hertz. And 0.4 meters. And that will be F equals 144 hertz. A violin string that is 50 centimeters long has a fundamental frequency of 440 hertz. What is the speed of waves on this string? The velocity equals, that's listed, we're going to plug in, n is 1, and we're going to get 440 meters per second. Figure 17, vibrations in shape give each instrument a different harmonic series. So just look at this, just with one picture, there's various instruments. Well, tuba and trumpet. Trumpets, saxophones, and clarinets are similar to a pipe closed at one end. For example, although the trumpet shown in figure 17 has two ends open, the player's mouth effectively closes one end of the instrument. In a saxophone or a clarinet, the reed closes one end. Despite the similarity between these instruments and a pipe closed at one end, our equation for the harmonic series of pipes does not directly apply to such instruments. One reason the equation does not apply is that any deviation from the cylindrical shape of a pipe affects the harmonic series of an instrument. Another reason is that the open holes of many instruments affect the harmonics. For example, a clarinet is primarily cylindrical, but there are some even harmonics in a clarinet's tone at relatively small intensities. The shape of the saxophone is such that the harmonic series in a saxophone is similar to that in a cylindrical pipe open at both ends, even though only one end of the saxophone is open. These deviations are in part responsible for the variety of sounds that can be produced by different instruments. This is table 4, harmonics of a tuning fork, a clarinet, and a viola at the same pitch. Harmonics account for good quality or timbre. Table 4 shows the harmonics present in a tuning fork, a clarinet, and a viola, when each sound the musical note a natural. Each instrument has its own characteristic mixture of harmonics at varying intensities. The harmonics shown in the second column of table 4 add together according to the principle of superposition to give the resultant waveform shown in the third column. Since a tuning fork vibrates at only its fundamental frequency, its waveform is simply a sine wave. Some tuning forks also vibrate at higher frequencies when they are struck hard enough. The waveforms of the other instruments are more complex because they consist of many harmonics, each at different intensities. Each individual harmonic waveform is a sine wave, but the resultant wave is more complex than a sine wave because each individual waveform has a different frequency. In music, the mixture of harmonics that produces the characteristic sound of an instrument is referred to as the spectrum of sound. From the perspective of the listener, this spectrum results in sound quality or timbre. The timbre, the musical quality of a tone resulting from the combination of harmonics present at different intensities. A clarinet sounds different from a viola because of differences in timbre. Even when both instruments are sounding the same note at the same volume, the rich harmonics of most instruments provide a much fuller sound than that of a tuning fork. Reverberation. Auditoriums, churches, concert halls, libraries, and music rooms are designed with specific functions in mind. One auditorium may be made for rock concerts, while another is constructed for use as a lecture hall. Your school's auditorium, for instance, may allow you to hear a speaker well, but make a band sound damped and muffled. Rooms are often constructed so that sounds made by a speaker or a musical instrument bounce back and forth against the ceilings, walls, floors, and other surfaces. This repetitive echo is called reverberation. The reverberation time is the amount of time it takes for a sound's intensity to decrease by 60 decibels. For speech, the auditorium should be designed so that the reverberation time is relatively short. A repeated echo of each word could become confusing to listeners. Music halls may differ in construction depending on the type of music usually played there. For example, rock music is generally less pleasing with a large amount of reverberation, but more reverberation is sometimes desired for orchestral and choral music. For these reasons, you may notice a difference in the way ceilings, walls, and furnishings are designed in different rooms. Ceilings designed for a lot of reverberation are flat and hard. Ceilings in libraries and other quiet places are often made of soft or textured materials to muffle sounds. Padded furnishings and plants can also be strategically arranged to absorb sound. All of these different factors are considered and combined to accommodate the auditory function of a room. The intensity of each harmonic varies within a particular instrument, depending on frequency, amplitude of vibration, and a variety of other factors. With a violin, for example, the intensity of each harmonic depends on where the string is bowed, the speed of the bow on the string, and the force the bow exerts on the string. Because there are so many factors involved, most instruments can produce a wide variety of tones. Even though the waveforms of a clarinet and a viola are more complex than those of a tuning fork, note that each consists of repeating patterns. Such waveforms are said to be periodic. These repeating patterns occur because each frequency is an integral multiple of the fundamental frequency. Fundamental frequency determines pitch. As you saw in section 1, the frequency of sound determines its pitch. In musical instruments, the fundamental frequency of a vibration typically determines pitch. Other harmonics are sometimes referred to as overtones. In the chromatic half-step musical scale, these are 12 notes, each of which has a characteristic frequency. The frequency of the 13th note is exactly twice that of the first note, and together the 13 notes constitute an octave. For stringed instruments and open-ended wind instruments, the frequency of the second harmonic of a note corresponds to the frequency of the octave above that note. So far, we have considered the superposition of waves in a harmonic series, where each frequency is an integral part of the fundamental frequency. When two waves of slightly different frequencies interfere, the interference pattern varies in such a way that a listener hears an alternation between loudness and softness. The variation from soft to loud and back to soft is called a beat. A beat, the periodic variation in the amplitude of a wave that is the superposition of two waves of slightly different frequencies. Conceptual challenge. There are three. Concert violins. Before a performance, musicians tune their instruments to match their fundamental frequencies. If a conductor hears the number of beats decreasing as two violin players are tuning, are the fundamental frequencies of these violins becoming closer together or farther apart? Explain. 2. Tuning flutes. How could two flute players use beats to ensure that their instruments are in tune with each other? 3. Sound from a guitar. Will the speed of the wave on a vibrating guitar string be the same as the speed of the sound waves in the air that are generated by this vibration? How will the frequency and wavelength of the wave on the string compare with the frequency and wavelength of the sound waves in the air? The answers. Number 1, concert violins. The fundamental frequencies are getting closer together because if the number of beats heard each second is decreasing, the two waves are closer to being completely in phase at all points. Tuning flutes. When the two flutists play the same note, the number of beats heard each second is the frequency difference between the two flutes. If one of the flutes is adjusted until no beats are heard, the two flutes will be in tune with each other. 3. Sound from a guitar. The speed of the sound wave in air will not be the same as the speed of waves on the string. There is no frequency change because the vibrations are still occurring at the same rate. So the wavelengths must change with the wave speed. V equals lambda f. Figure 18. Beats are formed by the interference of two waves of slightly different frequencies traveling in the same direction. In this case, constructive interference is greatest at T2 when the two waves are in phase. Sound waves at slightly different frequencies produce beats. Figure 18 shows how beats occur. In figure 18a, the waves produced by two tuning forks of different frequencies start exactly opposite one another. These waves combine according to the superposition principle, as shown in figure 18b. When the two waves are exactly opposite one another, they are said to be out of phase, and complete destructive interference occurs. For this reason, no sound is heard at T1 because these waves have different frequencies after a few more cycles. The crest of the blue wave matches up with the crest of the red wave, as at T2. At this point, the waves are said to be in phase. In phase. Now, constructive interference occurs and the sound is louder because the blue wave has a higher frequency than the red wave. The waves are out of phase again at T3 and no sound is heard. As time passes, the waves continue to be in and out of phase. The interference constantly shifts between constructive interference and destructive interference, and the listener hears the sound getting softer and louder and then softer again. You may have noticed a similar phenomenon on the playground swing sets. If two people are swinging next to each other, next to one another, at different frequencies, the two swings may alternate between being in phase and being out of phase. The number of beats per second corresponds to the difference between frequencies. In our previous example, there is 1 beat, which occurs at T2. 1 beat corresponds to the blue wave gaining one entire cycle on the red wave. This is because to go from one destructive interference to the next, the red wave must lag one entire cycle behind the blue wave. If the time that lapses from T1 to T3 is 1 second, then the blue wave completes one more cycle per second than the red wave. In other words, its frequency is greater by 1 hertz. By generalizing this, you can see that the frequency difference between two sounds can be found by the number of beats per second. Section review number 1. On a piano, the note middle C has a fundamental frequency of 262 hertz. What is the second harmonic of this note? What I'll do is I'll run through these quickly, 4 seconds per slide. Try to keep up. There's always the pause button. Here's the given, 262 hertz, and the F2 would be 2 times that, so it would be 524. Yes, 524 would be F2. If the piano wire in item 1 is 66 centimeters long, what is the speed of wave on this wire? So you're going to need some kind of equation possibly. You want to write down your data anyway. So your given is simply 0.66 meters long. Don't forget to do the conversion. There's your equation. And that's you're plugging in. Notice the 0.660 meters. And the answer is 348 meters per second. A piano tuner uses 392 hertz tuning fork to tune the wire for G natural. Here's 4 beats per second. What are the 2 possible frequencies of vibration of this piano wire? Let's see. So it'll be plus or minus 4 from 392. So it's going to be 388 hertz and 396 hertz. In a clarinet, the reed end of the instrument acts as a node, and the first open hole acts as an antinode. Because the shape of the clarinet is nearly cylindrical, its harmonic series approximately follows that of a pipe closed at one end. What harmonic series is predominant in a clarinet? The odd harmonics. The odd harmonics. Okay. Which of the following are different for a trumpet and a banjo when both played notes at the same fundamental frequencies? A. Wavelength in the air of the first harmonic, which wavelengths are present, intensity of each harmonic, and sound, speed of sound in air. Looks like it's going to be the middle of the infield. Which harmonics are present and intensity of each harmonic? Okay, section 1, key ideas. The frequency of the sound wave determines its pitch. The speed of sound depends on the medium. The relative motion between the source of waves and an observer creates an apparent frequency shift known as the Doppler effect. I'll leave this on for a couple seconds to see if you want to take some notes. Okay, section 2, sound intensity and resonance under key ideas. The sound intensity of a spherical wave is the power per area. Sound intensity is inversely proportionate to the square of the distance from the source because the same energy is spread over a larger area. Intensity and frequency determine which sound is audible. Decibel level is the measure of relative intensity on a logarithmic scale. So it is a logarithmic scale. Section 2 continued. A given difference in decibels corresponds to a fixed difference in perceived loudness. A forced vibration at the natural frequency produces resonance. The human ear transmits vibrations that cause nerve impulses. The brain intercepts these impulses as sounds of varying frequencies. Again, I'll leave it up if you want to take some notes. We have one slide left. That would be section 3. Harmonics are, this is harmonics. Harmonics are integral multiples of the fundamental frequency. A vibrating string or a pipe open at both ends produce all harmonics. A pipe closed at one end produces only odd harmonics. The number and intensity of harmonics account for the sound quality of an instrument, also known as the timbre. And we're off.